Okay, hello everyone. Welcome to this week's CHIME FRB Journal Club. We have another external speaker this week, which is very exciting. So our speaker is Liam Connor, who is currently at Caltech, and he's going to talk to us about this paper that he wrote with Vikram Ravi about a detection of circumgalactic gas with fast radio bursts. So take it away, Liam.
Thank you, Emily. So yeah, I'll be talking about this paper that we put out about 1 month ago. And I think a number of you probably saw me discuss this at FRB 2021, where I gave a late breaking news talk. So I'll try not to be too redundant, but I'll go over the basics and go through the figures in the paper. But also feel free to interrupt me throughout. Given it's your guys' data, I also have lots of questions for you guys, and I'd love to have a more in-depth discussion either during or after this.
Do you have a way to monitor whether, do you have a way to monitor the raised hands or anything like that?
I probably won't be able to because I'm in presenter mode now.
Okay, I can keep an eye on it.
Okay, thanks. Yeah, so in this paper, we claim to have detected circumgalactic gas using FRBs from the CHIME FRB catalog 1. The setup is as follows. You have some distant fast radio bursts. Some of these sightlines are going to intersect foreground galaxies whose dark matter halos are filled with diffuse gas. And this diffuse gas plays a really outsized role in things like galaxy formation, star formation. There's lots of interesting feedback. And despite its importance, it's really hard to detect because it's so diffuse. And when this gas is around individual galaxies, we call this the circumgalactic medium, the CGM. When it's sort of shared between galaxies in a galaxy group, it's the intra-group medium. And then for clusters, it's the ICM, the intra-cluster medium. So even since the inception of the FRB field, it was hoped that FRBs could be used as a probe of this gas. Because FRB, the dispersion measures of FRBs provide this really clean, model-independent measurement of the total electron column density. So going back to this well-known paper by Matthew McQuinn in 2013, called Locating the Missing Baryons with Extragalactic Dispersion Measures. Xavier Prochaska has a couple papers on this, Vikram Ravi, lots of others. And the reference to the missing baryons comes from the fact that, through Big Bang nucleosynthesis and the CMB, we have a pretty good handle on omega B, the density of baryons in the universe, to less than 1%. But we don't have a great idea of the actual distribution of these baryons in the universe, especially when it comes to their distribution around galaxies and within galaxy groups. Now, the thing that these three papers that I'm showing here have in common is that they all assume that one would need really precise localizations of fast radio bursts to start probing CGM. And the idea is basically just that most of the optical depth, the probability that you're going to actually intersect a foreground galaxy comes from really distant galaxies because this optical depth scales as distance. And so if you have a cosmological FRB, it probably intersects a cosmological galaxy. And the angular size of that galaxy is going to be really small, which means you need a precise localization to actually unambiguously associate it with the foreground galaxy. And so people assume that you would need ASCAP localizations or CHIME without rigors or DSA or whatever. So our claim in this paper is that actually the CHIME FRB catalog 1 is large enough that you can start doing this if you just focus on nearby foreground galaxies, so galaxies in the local universe. And so to this end, we took the Gravitational Wave Galaxy Catalog, GWGC, which is quite complete and includes galaxies up to 100 megaparsecs. We did a further cut on this, including only galaxies within about 40 megaparsecs, and which are brighter with brighter Bmags than minus 18.5. And this is because at 40 megaparsecs, a typical L-star galaxy is going to have an angular size that corresponds roughly to the CHIME localization region. And then we take the CHIME catalog and we ask which, if any, intersects within a virial radius of these foreground galaxies. And if they do, does that subset of intersecting FRBs have higher dispersion measure on average than those that do not? So we used 3 different intersection criteria to decide whether or not a CHIME FRB actually intersected one of these GWGC galaxies. The one that I use in the paper and that I'll be using mainly today is number 1, where we say, if the impact parameter of the FRB is less than some threshold value, B perp, scaled by the virial radius of that galaxy, virial radius corresponding to the halo mass to the 1/3, then that counts as an intersection. You can also do it in a mass agnostic way, just say if R perp is less than some threshold parameter B perp, and you can do it in a way that depends on the confidence intervals that you guys have provided in those localization H5 files, which is the third way. And you can say, for example, is the median impact parameter within the 68% confidence region less than some value? So all 3 of these methods produce similar results, but the one I'll be using in this talk is number 1. So if you do this, you find that the number of galaxy CHIME FRB intersections scales quadratically as you'd expect, with roughly the values that you would have calculated if you were just doing a simple back of the envelope optical depth calculation. So you see about 24 intersections for impact parameter less than 250 kiloparsecs. And here's a visualization of those intersections if we freeze B perp at 250 kiloparsecs. So what you're seeing here, the little blue dots are CHIME FRBs. By the way, we only include once-off events just in case they have a different distance or DM distribution than repeaters. So the blue dots are the non-intersecting CHIME FRBs, and their color corresponds to the mean dispersion measure of that set. The colored dots, the small colored dots, are CHIME FRBs that intersect foreground galaxies, and they're color-coded by their dispersion measure. And the big gray circles are the foreground galaxies that are intersected, where the size of the circle corresponds to their modeled virial radius. So what you'll notice is that most of the galaxies, or most of the FRBs that intersect a galaxy that belongs to a group. And most of these belong to the local group. So the local group is the Milky Way, M31 and M33. So it's worth just noting that when we try to interpret the results later. And this is not surprising, by the way. About 50% of galaxies at redshift 0 live in galaxy groups. Okay, so now we want to ask, do those intersecting FRBs have larger DM than the non-intersecting ones? And so here I'm freezing B perp at 250 kiloparsecs. Again, that's the threshold impact parameter. And then I'm asking, does the green histogram have a higher mean in a statistically significant way than the black histogram? And the answer is yes in this case. So to test the significance of this, we use a 2-sample one-sided t-test. So t-test is for looking for differences in means between distributions. It's one-sided because we're only asking the question, are the intersecting FRBs larger in DM? Oh, I think Mohit has a question.
Hey, Liam, I can ask that question once you complete describing this figure.
Go ahead, Mohit.
Can you hear me?
It's very faint.
Okay, just give me 2 minutes. Please explain this figure and I'll make sure that my audio is fine.
I heard explain the figure. Sounds good. So yeah, we find a p-value for this t-test of about 1%. If you change B perp and use a tighter threshold impact parameter of 200, it's also statistically significant. If you use 150, now the p-value is 10 to the minus 3. So if you're uncomfortable with just trusting these p-values for the t-test, you can try something else, which is resampling the data. So what I'm showing here is the signal itself in the thick black dotted curve, and the left y-axis are p-values. And you can see it goes from about 10 to the minus 3 up to no longer being statistically significant by about B perp of 400 kiloparsecs. As you would expect, you should expect this signal to go away for sufficiently large B perp. And then in the background, the faint gray curves, those are sort of realizations in a jackknife test where we've shuffled the CHIME dispersion measures randomly. And then we've drawn the same number of intersections from those reshuffled dispersion measures, and we've asked, do any of them have p-values as low as what we see in the actual data? Or do any of them have DM excesses that are larger than what we claim to see in the data? And the answer is not really, or at least it's very rare. So if you look on the right, that's the cumulative number of p-values. It's a p-value distribution for these random shufflings. And we find that in only 0.2% of cases do the reshuffled CHIME DMs have as large of an excess as what's seen with the actual intersecting FRBs. Now, maybe I'll pause for a second and allow for questions, because I feel like these two plots can be kind of confusing.
Yeah, Mohit, do you want to try again?
Yeah, can you hear me now?
Yeah.
Sorry for the.
Oh, no, now it's very faint again.
Liam, actually, I have this question regarding figure where you actually showed it. So the first question I actually had just looking at the figure was why you actually used t-test, because I just noticed that the distribution doesn't look like normal, and t-test assumes normal distribution. So why don't you use a non-parametric test to actually estimate the p-values?
Yeah, that's a fair question. I thought with a t-test, it's the distribution of means ought to be normal.
Now, so I understand doesn't mean that the data itself should follow normal test, but it's the observed samples that should follow normal test. But I actually don't see, even in that case, you expect your observed samples to follow normal test, normal distribution as well, because DM Milky Way is different for different sight lines and all. Means it's just, I just had a question. If you have non-parametric test, why don't you?
Yeah, that's fair. There is a non-parametric like generalization of the t-test, but that's effectively what the jackknife test is, right?
Yeah, and regarding jackknife test, this is from my personal experience, not here, but when I was doing masters, I found that it is always better to after jackknife, when jackknifing or bootstrapping, estimate p-value based on the test statistics of the distribution rather than using p-values individually for each realization. And I found that in my master's thesis, I found different results. So I'm just curious that whether that effect would be relevant here.
Well, one of the reasons I'm sort of confident in the t-test is that the distribution of p-values that you get out from the jackknife is what you would expect from random DMs. So it's effectively uniform. In other words, if you get a p-value in the t-test that's 5%, then you'll find that only 5 out of 100 of those jackknife realizations is greater than the excess that you see.
Okay. Yeah, I need to think a little bit over, but if you're saying this, it makes sense. But I'm just, my second point is basically that instead of using the distribution of p-values, I'm just wondering, would it be more robust if if you first estimate the distribution of test statistics, means t-test statistics, and then estimate p-value? Because in my past experience, I found that the confidence level on p-values when you just use the p-value distribution is different when you basically estimate p-value from the test statistics distribution. Does that make sense? Or I can just
yeah. I see what you mean, but I really do think that this like we're sort of calibrating it against the resampling. Actually, the statistic that we quote in the new version of the paper uses this jackknife test, where we find that only in 0.2% of cases is a randomly drawn excess as large as the one we see in the CHIME data.
Okay, I see your point. I have another question, but I think Amanda should ask. I'm really sorry, but thank you very much.
Sure.
Yeah, so firstly, I'm sorry if I missed this. And also I'm sorry if Mohit asked, because I'm really having a hard time hearing. But so firstly, what DMs are you using? Excess DMs? Like, are you subtracting up a model, or are these the raw like measured DMs?
Oh yeah, good question. So we use three DM fields. We use the observer, that's called like DM fit B or something. And then in the actual paper, we use DM excluding any 2001, as well as any DM excluding YMW. And in all three cases, the signal remains. We also, I should have mentioned that we exclude everything within 5 degrees of the galaxy. And we've tried varying that cut in galactic latitude, and it doesn't really change things.
Okay, interesting. That's really good to know. And then also, so yeah, I guess this might have been what Mohit just asked, but are you interpreting the fact that your t-test says that your results are significant at about the 1% level, but then your jackknife test suggests like it's more significant as the t-test being conservative? Like that's a reasonable agreement?
I think they're actually consistent. In this case, this histogram on the right I'm showing is only 150 realizations, but I've done a larger one. Where I've done 1,000 realizations, and the p-values basically correspond to the rareness of seeing realizations as large as the DM excess that we see in the data.
Okay, yeah, thanks so much.
Okay, cool. Oh yeah, and then I should also mention that Keo pointed out that we could actually try to remove the DM selection function that you guys presented in the first catalog paper. So we did that, and it doesn't change a whole lot, but it boosts the signal a little bit, which I think we would have expected because of the down weighting of the large DMs. Okay, and then just to go over some of the test cuts, resamplings that we did, because the signal is larger than what we would have expected, I was definitely quite skeptical when we first ran this analysis, and so tried a lot of different things to make the signal disappear. And it really only disappeared in the cases where we expected it to. So for example, if you take a distance cut, instead of doing everything within 40 or 50 megaparsecs, and you say everything beyond 50 megaparsecs, then the signal goes away, and that's because at that point you're getting false associations with foreground galaxies. The foreground galaxies are too small in angular scale to unambiguously associate with a CHIME localization region, and therefore the ones that you highlight as having intersected a foreground galaxy probably didn't. And so p-values are greater than 5% or 10% in that case. We changed the luminosity threshold. So remember I said we only included Bmags less than minus 18.5. You can sort of turn that knob and the signal remains galactic latitude cuts, different DM fields. When you scramble the DMs, when you scramble the positions, the signal goes away. And in these 3 different selection criteria for the sort of best guess for the position of the CHIME FRB, the signal remains as well. Now, that doesn't mean we haven't missed something, but I've sort of exhausted all the different ways that this could have gone wrong, in my mind anyway. Okay, so we've talked about the statistical significance of the excess or the difference in DM, but we should talk about the amplitude now. So this is a plot of DM excess. So the average DM of the intersecting FRBs minus the average DM of the non-intersecting FRBs as a function of this choice of threshold impact parameter Bperp. So you can see below maybe 300 or 350 kiloparsecs, you get quite a large excess, a couple hundred units of DM. And this is surprising. We would have expected 15 to 30 or 40 parsecs per cubic centimeter. And it's worth noting, by the way, that there's a lot less scatter in the curve than the size of the error bars, and that's because each point is highly correlated. So this should not be interpreted as like a free electron profile of the halos or anything like that. Okay, so keeping in mind that the signal is larger than we expect, it's worth looking at the actual galaxies that were intersected. So I mentioned before that most belong to groups. Actually, most of those belong to the local group, the M31 group. Now the signal persists if we exclude the local group, if we only use the subset of FRBs that intersects galaxies beyond, for example, a megaparsec. But most of the signal comes from the local group, I should emphasize. So we still get p-values less than 0.05 for impact parameters less than a few hundred, but the signal is weaker. And here's all galaxies again. So if we do a simulation where we just kind of do what people have done in the past, which is you take say an L-star galaxy, a Milky Way-like galaxy, with a dark matter halo of roughly 10 to the 12 or 10 to the 12.2. And then you plop on top of that a modified NFW profile or a beta profile for the free electrons. And then you pierce it with random sight lines, in this case, 24 random sight lines. And you take the average XSDM, so trying to simulate what we should have seen if all of these were just with individual field galaxies. You get a DMXS distribution that looks like this. And you can see in most cases, the XS is less than 50 parsecs per cubic centimeter. Whereas we see a couple of hundred units with large error bars, but still. And you can do this in a way where you actually weight by the something like the localization PDF. And again, you find that in most cases, you get significantly less than 100 units. And so the only way to make this make sense seems to be to have larger halo masses. So what you see here are those curves when you vary the dark matter halo mass, both for the MNFW profile and the beta profile. And only once you get up to the sort of halo masses of groups, 10 to the 12.5 to 10 to the 13.5, do we start seeing the DM offsets that correspond to the signal amplitude in the data. And again, here's another simple model. This is from Xavier's paper, Prochaska 2019, I think, where the blue curve is the CGM of an individual galaxy. The green curve is the CGM of a local group like galaxy, or the intragroup medium of a local group like Halo, and then the intracluster medium. And you see that the CGM for an individual galaxy falls off quite quickly. You have to be really close to it to get over 100 units. In the case of the intragroup medium, even out to a few hundred kiloparsecs, you're still well above 100 units of DM. And this is from the same paper. This is a model of the local group medium. You can see that the angular size is really enormous. And actually the local group medium is of order 1,000 square degrees. So if CHIME sees 20,000 square degrees, you might expect 1 in 20 CHIME FRBs to intersect with the M31 group, which means with 2,000 or 2,500 fast radio bursts, you could have 100 sources intersecting the M31 group, and you could really start to map things out. But this is a very simple model where they've taken, I think, a 10 to the 12.7 or so solar mass halo and plopped on top of it an MNFW profile. Here's a more empirical approach to mapping out M31, the local group medium. This is a recent result that used SZ and X-ray observations. And what they find is that there is really extended hot halo gas around M31 that's much more extended and much more massive than what you'd expect just from M31 itself. So if you look at the top left figure, that's the Compton Y parameter as a function of angular separation from M31. And the little purple curve is what you'd expect based on the known halo mass of M31. Whereas the black dots are the data, and the two models they fit to it are in yellow, a beta model. So it seems like spherically symmetric. And in blue, a model where you assume it's more cylindrical. So they find that the blue curve fits the data better, and that this suggests there's maybe a hot halo bridge connecting M31 and the Milky Way, such that when you're staring down the barrel of the shotgun, you get a lot of DM. And this is roughly consistent with our results as well. So if you take these X-ray observations and the SE estimates and you compute a DM from it, you get about 80 to 400 parsecs per cubic centimeter, which is of order the size of the excess DM that we've seen when you just isolate the LGM component of our signal. Okay, so to wrap up, we found that CHIME FRBs that intersect the halos of nearby foreground galaxies have statistically significantly higher DMs than those that do not. The excess that we see is larger than what we'd expect for individual CGM, and we attribute this in part to the fact that intragroup medium is expected to contribute significantly more DM than individual galaxies, and specifically the local group itself where we have this sort of special position within it. We might be looking down this hot plasma bridge, contributes a significant amount of this excess dispersion. As I alluded to a minute ago, the full collection of CHIME FRBs will be really interesting to play with, and maybe you guys have already done that. But having 4 or 5 times more sources will only make this more robust, or heaven forbid, falsify it. And then finally, clusters. Clusters are really exciting. There's no reason why, in principle, you couldn't do this exact same thing with clusters. It's a little harder because their volumetric density is lower, which means you're not going to have any that you know for sure are in the foreground. And so you have to be maybe clever statistically or something. But it's worth pointing out that with a cursory search, we found that the highest DM FRB in the CHIME catalog 1, whose DM is like 3,000 something, comes within a virial radius of a cluster at redshift 0.3. So that will be really exciting. And then if you weren't on the call yet, I wanted to say that I'm running the T-Talks this fall and winter, along with a couple other people at Caltech. So if you're a grad student or postdoc and you've got a fun result you'd like to talk about, please email me. Thanks.
Nice talk, Liam. All right, I'm sure we have plenty of questions. I already see Matt's hand up, so go ahead, Matt.
Hey, Liam, thanks for showing us this. Could you comment or put this in context of the CHIME FRB paper led by Masood of cross correlations that showed a DM excess of 400 with what would possibly be more distant FRBs with closer galaxies?
Yeah, sure. I was curious about that myself. So I guess the main takeaway from the Masood paper is that there's this cross correlation with galaxies at redshift 0.3 or so. But that some of them seem to have excess DM, which I think in that paper was interpreted as being local, like a subset of these having a significant local DM. I don't see why in principle it couldn't also be intersecting structure, right? Now, just to compare this directly with what we've done, I think those galaxy catalogs that Masood was cross-correlating against excluded the local universe. So like 2MPZ explicitly gets rid of things at redshift 0-ish. So our signal should not show up in their signal.
Right, but your signal gives a prediction for what sort of excess you should see in this sort of large scale structure correlation.
Yeah,
and I haven't done the math about impact parameter versus K value and so forth. And so I guess I'm wondering that, have you taken your result and interpreted them in terms of that, and does it make sense?
Not directly, but I think we should. And I think it sort of tilts the scale.
You haven't directly done it, or it doesn't directly make sense?
No, we haven't directly done that. I guess I was a little unclear on the interpretation of that excess DM within the CHIME FRB collaboration.
So I think Masood did that, right? Is my audio super soft?
Yeah, you're a little faint.
I wonder why that is.
If it helps, you're not nearly as faint as Mohit was.
I can hear you.
Can you hear me now?
Yes.
Yeah.
Great. So I think we did that interpretation. And so so first I wanted to say one thing. Liam, you say you weren't sure why that couldn't be intervening galaxies as opposed to actual associations of the FRB in the galaxy. And the reason for that is we don't correlate DM with galaxy number counts. We correlate FRBs themselves. So the counts of FRBs with the counts of galaxies. So an intervening galaxy would, it causes excess DM, but doesn't cause excess counts, FRB counts, right? Because you actually need the FRB itself to be clustered with the galaxy, and therefore they have to be at the same redshift. Now you can actually synthesize that with selection effects. Let's say you only detected high DM. Let's say you had some DM cut, and then you can selection effect your way into correlating these things. But that's not what we think is happening. We don't think our selection effects in DM are strong enough to do that. So that's why we think the FRBs we see are actually in the groups that are causing the excess DM. So there, in the interpretation, you should get, all the DM from that galaxy's group if it's in the group, and its cluster if it's in a cluster, and its CGM just because it's in a galaxy. Except for you only get half as much because you only have to get out of the halo. You don't have to get into the halo and then back out of the halo. So a factor of 2. But I think, back of the envelope, I think Masood's paper says that, with using the same sort of models that you're comparing to here, you expect, DMs of this of roughly this amplitude, order several hundred. Maybe you take a factor of 2 because they're not in because you don't have to come into the halo and back out. You just have to get out of the halo. But that being said, we won't just have groups. We'll also have a few clusters in there, right? And those clusters add huge contributions, right? As your plot showed. And of course you dilute that signal with some field galaxies and stuff that aren't in groups. But that's, I think, as you said, most of order unity are in groups. Matt, you're really shaking your head at me.
Oh yeah, I agree with your conclusions and so forth, but I think I disagree. We shouldn't be talking too much about Masood's paper, but instead about Liam's, but of us being able to reject the hypothesis that the FRBs are behind instead of inside. But let's talk about it, or that's between us, I guess. And for the question to Liam though, I more just wanted take not the interpretation of that paper, but the correlation and see where we stand. And I think the key thing here is the angular separation or the impact parameter, if that makes sense at all, once you crunch those numbers.
Yeah, well, I think one thing we'll start finding when we actually start localizing FRBs, or when you just use your bigger sample of CHIME FRBs, is that there's going to be a lot of variation, and it's not just going to depend on impact parameter, but the galaxy evolution history within that group, for example. And you're probably going to find that there's a lot of anisotropy, especially with galaxies and galaxy groups, which means that you can't just add 30 or 40 units per intervening halo. You might add 10 units one time and then 450 another time.
Okay, Mohit, you put your hand up.
Yep.
Thanks a lot. I'm sorry for last time. I don't know what was happening. So Liam, I actually have 2 questions. The first one is, can you go to your 4th last slide, I think. So when you remove local group and then you found the DMXS as a function of projected offset. Yeah, it's not 4th, I'm so sorry, but no, the one that it's DMXS versus, so there is one plot where you actually removed local group. Yeah, and here you said that even in this scenario, you got p-value greater, smaller than 0.1. And I'm sort of surprised looking at the error bars. Do you have the jackknife results for this?
Actually, I don't have a figure of the same jackknife cumulative distribution in this case, but yeah, I said the p-values are less than 5%.
Yeah, because looking at the error bars, and it's 1 sigma error bars, if I'm not wrong.
Yeah, that's right. So individual points are probably not statistically significant within 500 kiloparsecs, but we're asking the question in these different jackknife realizations, is the cumulative excess below some threshold larger than what we see in the data? And I'm saying that in fewer than 5% of cases, that's true.
And the way you're applying jackknife is you're again using same t-test statistics. It's just that you're sampling your data and estimating p-values.
You can do it without a t-test. You can do it just with the excess, right?
Yeah, but then you need to compare the distribution at the end. to
Yeah,
say.
yeah. I'm just saying I don't have the figure for that.
Okay, no, I'm just sort of yeah, surprised looking at this figure. And the second question is, when you're discussing about different selection effects that you have taken into account while performing this analysis. So I have said this thing. I actually asked the same question in the FRB 2021 meeting, but I wasn't able to express it in meaningful terms. So what I was saying is, as you know, that the exposure and sensitivity of the FRB, CHIME FRB field of view is different. And if you just look at M81 and M33 galaxies, these are like the sky locations where you have the maximum sensitivity. It's quite close to the zenith. So I'm just thinking, when you do the jackknife test, and this is something Alex has done in his paper, he actually just removed the area, only considered the area with sensitivity greater than equal to a certain threshold. And that threshold comes from the type of halo you are looking at. So I'm just thinking, if you add that effect, including that would definitely reduce the number of samples in your data, which I hope will increase the p-value, because you're increasing the number of samples, you're decreasing the number of data points. So I'm just thinking whether that effect would be significant in this analysis.
Yeah, I actually don't fully understand. So you're saying that, like, in the direction of the local group and in M81, you're quite sensitive. So
see, yeah,
for example, are overrepresented.
For example, if you estimate the threshold, fluence threshold, let's say, so if the fluence threshold in general, say at the declination of 10 or 15 degree is 5 Jansky millisecond, then relatively it would be 3 or 4 times more sensitive towards M31 or M33 halo. So in that case, if you believe that fluence, if you're more sensitive towards one direction, then you're more sensitive to detect fainter sources. And fluence, if it is proportional, if you can basically go one step forward and say that, okay, then you're more sensitive to detect far away FRBs in that direction.
Oh, I see.
Then
yeah, that's interesting.
Naturally expect higher DM sources in that direction.
Yeah. Oh, that's interesting. Yeah, we had not considered that effect. But if there is a strong fluence DM anti-correlation, and you really are significantly more sensitive to lower fluence FRBs in these particular directions, then yeah, you would have higher DMs.
Yeah, I think these effects will go on when you have larger sample. I completely agree with you. Like with second catalog of FRB, you don't actually need to worry about all these small effects.
Yeah, that's interesting. I'm gonna look into that.
Yeah, so one of the jackknives we often, or at least Masood used to that at least at first order deals with that, is to shuffle not just the DMs at fixed locations, but to shuffle the RAs of all our exposure in the RA direction is relatively uniform, not perfectly, right? Of course, but if you just randomize all the RAs of the CHIME detected FRBs, leave the DMs and the DEX the same, then you can check for that.
Yeah, interesting. Okay. So I think that, I mean, the number of intersections that we have with the local group is consistent with the back of the envelope that I mentioned before. It seems like about 4% of CHIME FRBs intersect the local group. So 10 out of 500. Yeah, that's interesting. It's good.
Maybe one way to look at the sensitivity issue is to do a cut on the zenith angle, something like plus or minus 20 from say a deck of our latitude, which is 49-ish. That should be a pretty flat, like it's our sensitivity profile is kind of ripply and flat within that region.
Yeah, so can I ask, like, oh, there's a lot of feedback. Internally, at what point will you be doing science with the full catalog? Or is it going to be like there was catalog 1 and then catalog 2, which is larger by some factor, and you're okay with analyzing that because you've got the biases and selection functions sorted or whatever? Or are you at the point now where you can just analyze the FRBs that come in every day?
I think we're always planning on doing it in batches. So I mean, I think we'll define. We have to define a catalog 2, but once we define a catalog 2, we will update our statistical analyses and invent new ones and copy yours on bursts up to that date and always have a cutoff. I think that's just a logistical strategy rather than anything deep, but that's what we had in our mind, I think.
Nice. And then another question I have for you guys is, has with better modeling and better understanding of the beams, as well as a larger fraction of detections that have a baseband dump, is the localization region like shrinking over time for the typical CHIME FRB? And will catalog 2 have like 2x or 3x smaller localizations?
I think the big one there is the baseband localization. There are, as was mentioned in the even without the baseband dumps, like as was mentioned in the Magnetar paper, you can model sort of the intensity spectra and the multi-beam detection to try to do a lot better than what we published in the catalog. And that does win you, a factor of 2 or 3. But I think the baseband localization wins you more than a factor of 2 or 3. So I think that's a way of really getting a slam dunk on analyses like these.
Yeah.
I actually had a question. So you finished your talk with clusters ! So I haven't actually looked at the numbers. What is the filling fraction of how many clusters are nearby that that subtend sort of arc minutes in the sky or degrees in the sky?
Yeah, how nearby are you thinking? Like nearby enough that you know that the median FRB is behind them?
No, I'm not thinking the median FRB. I am thinking nearby enough that the impact parameter is relevant on the scale of localizations. So let's say, I mean, the catalog 1 has, 10 arc minute localizations, and that could get, with baseband, that could get better by a factor of a few, right? But I mean, a Redshift 1 cluster is going to be out of the question for, even if you thought the FRB was behind it, you still don't have the localization good enough to do this analysis, right?
Yeah. I mean, you can go really far because they're 1 or 2 megaparsecs. So they're already 10 times larger in virial radius than the CGM of individual galaxies, and 100 times larger in filling factor. They're also significantly less common, obviously, but yeah, I think you'll end up with a batch that's like 10 to 30 if you do this exact same analysis that I've done with galaxies.
I can just give you quickly an answer to that question. So coma cluster, it is at 100 megaparsec. So it's I think the angular size of coma cluster, and it is visible to CHIME, by the way, and is around 30 arc minutes or 40 arc minutes if you believe the first turnaround radius. So yeah, you can do, and I think Sculptor ASCAP can actually do a very good job with Sculptor cluster, and Virgo cluster as well. It's way more. It's 2 degrees around. Again,
So from a size point of view, you can go to a few hundred megaparsecs, I guess. And then the problem is filling factor that, just a small number of FRBs happen to intersect it because they're rare.
I think you can go beyond a gigaparsec from when I've done these numbers, but I might be wrong.
Wow.
Yeah, so what do you guys think of this statement? The DM distribution that you've published in the CHIME FRB catalog 1 seems to indicate that high DM events are not just very distant high luminosity events. That actually there's probably a cutoff in the luminosity function, and therefore the really high DM events are either locally dispersed or they intersect clusters or groups. Is there any internal consensus on that?
We can't refute it.
Yeah, it sounds fully plausible to me.
And so depending on like how wide the distribution of local DMs is, like truly local, you could compare that with what you expect for cluster and group intersections.
Yeah.
Yeah, I mean, I think these distributions are starting to take are just starting now to take form, right? Like, you know, I mean, we have the ASCAP localizations and redshifts, right? And you know, we know how far off the McCart relation they fall,
Mhm.
and that scatter has to be eaten up by large scale structure and local components, and it's starting to look like the large scale structure component is not small compared to the local component, which is in itself, you know, nice,
That's
right?
great.
It's great. It would be really great if the local component turned out to be, you know, 10 RMS, right? But I think they're going to be. Seems like we're going to have a coincidence problem that they might be of roughly the same order of magnitude.
Mhm.
Actually, Liam, I have a question regarding the definition of DMIGM and DMCGM you have used in your paper. And I think it's a general question because if you look at McQuart relation or even McQueen simulation or McQueen 2013 simulation, he accounted for all this intersections through different halo. It's galaxy halos and I think even cluster halos as well, or group halos. I'm sorry, not cluster, but group halos definitely. But you actually separated DMCGM from DMIGM, and then you said that DMIGM is constrained by quart relation, which actually takes into which accounts for all these halo intersections as well.
Yeah, I mean, if there were no IGM, you would still have a McCord relation, just because the optical depth increases with distance. So distant events are more likely to intersect a foreground galaxy, and therefore they're going to have CGM contribution, even if the IGM has 0% of the plasma in the universe. Do you just mean like one of the introductory sentences where we say, or that equation where you're breaking these down?
Yeah, I mean, I think my question is, I think in IGM contribution, we somehow takes into account the contribution of the halos as well. So I'm sort of, I'm confused whether we are taking the contribution of the halo twice in our calculations. Because
no, I don't think so.
Because after reading your paper, I actually went to this consensus on the baryons, this paper by McQuart et al. And they have actually taken into account halos of mass 10 to the power minus 12 solar masses and 10 to the power minus 13. There is a plot in their paper for different halo masses. They have estimated different parametric form of DMIGM. So I was just thinking, what is the consensus in the field? Like, how should we actually take these two different contributions to the DM separately, or we just sum up them into one?
Well, again, I think the McCord relation itself is really just this empirical observation that DM is proportional to redshift. And then when you're trying to interpret that correlation, you're asking what fraction of this is from the IGM and what fraction is from intersecting CGM. And this is the whole question. This is the whole game when it comes to using FRBs to probe the diffuse gas in the universe.
So when I said McQuart relation, I'm not just thinking about the straight line or a single line. I'm just thinking about this whole region in redshift versus DM space. And so, yeah, I'm sort of just confused whether in DMIGM we actually somehow takes into account the contribution of the halo intersections as well. But yeah, I'll look into this further, I suppose. Maybe just my confusion.
Okay, are there any other questions for Liam? All right. If not, then if people have further questions, they can always get in touch, send you an email, follow up there. But otherwise, we will end the journal club today. Thank you so much, Liam, for coming to speak to us and answering all of our questions and the nice back and forth. And we will put the recording online for other people. So I will stop the recording now.